Hey, hi everyone. So let's talk about the logistic growth function today. The logistic growth function today. First, let's start off with our conditions. We have constants A, B, C. They're greater than 0. Right, so they're positive constants. Okay, I'm being OCD a little bit. And then we have B is less than 1, so that constant is less than 1. Right, then we can say that we have the function f of t is equal to c over 1 plus a e to the power of negative bt, where t is equal to the amount of years. Not years, but it could represent any amount of time. Alright, so let's go ahead and change t. Instead of it to years, it's time. T equals time. Okay, so where did this function come from? Like, why this function? Why do we even need it? Like, we had exponentials. We had an exponential growth function. Alright, so if you look here, an exponential function, a regular exponential function, if we had, y equals, let's talk about e to the power of x. Alright, let's look at that exponential function if we have e, base e. So it's something that kind of goes on forever. We had something that looked like this. But for a logistic growth function, logistic growth, however, on the other hand, we have it, instead of it going infinitely forever, the logistic growth function actually takes into account certain population, like growth factors, things that can inhibit population growth. Like, let's look at like human civilization population growth, right? So sometimes a war might start, or famine, some other factors where population can't grow anymore, because it's not always going to be exponential. It's going to have a stopping point at one point. And exponential growth shows us that it tends not exponential, logistic growth. So it'll start at one point, and then it'll start to go, and then it starts to kind of destabilize or start to slow down at one point. So logistic growth, our graph will look something like this. Right? And that's where they derived the formula from. They're like, well, if you use this formula, well, this is going to take into account population growth factors, or factors that inhibit population growth is probably the correct way to say it. Alright, so let's go ahead and get started. Let's do an example with logistic growth. City's population in millions is modeled by f of t with the given equation, where t is the number of years since 2000. So first things first, graph the function. I actually have the graph right over here. It's the first thing I've graphed. Right? And this is going up by what? It's 2 divided by 4, so it's going up by 0.5, 1, 1.5, and then 2. Right? So here's my function. I have my units going up by 0.5 on the left, and then on the right, I have it going by, this is 25, and then I have 50, and then 75, 100. So just a reminder that t is the number in years, and our output is in millions. Okay, so here is the graph of our function. As you can see, it stops right about here. Growth stops when our line is it's starting to look horizontal. So that's when our graph is, or our population stops. Or it's not growing heavily. Now let's look at part 2 of our question. What is the horizontal asymptote? Well, the horizontal asymptote, as you can see, it's very close to 1.5. And from our graph and from the way that logistic growth problems work, is that it's actually the number on top, right? That is going to be your horizontal asymptote. Right? And if I were to zoom in, you'd see that this is actually y equals 1.432. Right? So our asymptote is y equals 1.432. And the third part of our question, what will be the maximum population? So the max population that we can have is right before y equals 1.432, because that's where it reaches, and that's where it's constant from there on out. And so I want to see, what is this value? All right, my population, right? The maximum population that I can reach, well, we found that that value is y equals 1.432. And just remember that these are in millions. So the max population that we can ever have is 1.432 million, which if we rewrite it, it's actually written as 1,432,000. Okay, so this is our max population. Let's go ahead and box our answers so far. And for the fourth one, I'll write this out here because this one requires a little bit more of work. According to the function, when will the city's population reach 1 million? All right, so I want to know when will I reach 1 million. So I'm looking for the time here. So I will set the whole function equal to 1 because my output is in millions, 1.432 all over 1 plus 1.05 e to the negative 0.32t. Okay, and then let's move the 1.432 to the other side. So I would multiply that by 1 over 1.432. 1 divided by 1.432 is equal to 1 over 1 plus 1.05 e to the negative 0.32t. And we can go ahead and flip, all right, reciprocate both of them. So it's 1.432 is equal to 1 plus 1.05 e to the negative 0.32. Move the 1 to the other side. Now these are just algebra rules what I'm applying. So I have 0.432 here, and this cancels out, and I have 1.05 bring down 1.05 e to the power of negative 0.32t. Divide by 1.5 on both sides. Okay, and I'll keep mine like this on the left-hand side, and then we have 0.432 over 1.05 equal to e to the negative 0.32t. Now we have e, so I'd have to take the natural log of both sides. When I take the natural log of both sides, I have natural log of e to the negative 0.32t equal to the natural log of 0.432 over 1.05. Okay, now I'm going to scooch this down so we have more work, so you can see my work clear. Alright, take the natural log, bring the power down to the left-hand side. Alright, so natural log of e, that's just equal to 1. Alright, so this is equal to 0.32, negative 0.32t, and the natural log of 0.432 over 1.05. Divide by negative 0.32 on both sides. 0.32, both sides. Then you are left with t on its own. Alright, so I have t is equal to the natural log of 0.432 over 1.05 over negative 0.32. That actually is approximately 2.77, and t was in years. Remember, this is in years. And you can actually round here. So this is the years since 2000, and you can say that this is approximately 3. You can round up, so you would do 2000 plus 3, leaving you with 2003. So according to this function, when will the city's population reach 1 million? That is in year 2003.